And you're going to introduce me, John?
Yes, I will. I'll still do all the introductions. Good morning, everyone, or good afternoon. Welcome, everyone, on behalf of the Southern Alliance for Clean Energy. I'd like to thank you for joining us on today's webinar, Measuring Climate Benefit, Carbon Life Cycle Analysis for Bioenergy. This is the fourth of 5 webinars in our Southeast Biocarbon Initiative webinar series. To learn more about this series, please visit our website at www.cleanenergy.org and search for biocarbon, one word. My name is John Bonnetz, and I'm the Staff Biomass Policy Specialist for Southern Alliance for Clean Energy. Before we get started today, a few words on how this works. The Google Plus Hangout format is quite user-friendly and self-explanatory for those watching. To ensure sound quality, all attendees are muted through this presentation. We encourage you to please type in any questions you may have in the little box that says, "Say something." For those watching the live feed through YouTube, you can type your question in the comments space. We will answer questions at the very end of this presentation today, and in addition to the live broadcast, the entire webinar will be video recorded and posted to the YouTube account called SACE Clean Energy. For those of you not familiar with Southern Alliance for Clean Energy, we are a regional nonprofit organization focused on promoting responsible energy choices that create global warming solutions and ensure clean, safe, and healthy communities throughout the Southeast. We are a membership organization, and I would like to acknowledge and thank our members on this call and on this webinar today, and encourage those of you who are not members to please join us today. Now, to begin the presentations, I do need to apologize. I've had some problems with importing some of the files. It's a PC to Mac problem, and Jesse Daystar, one of our 2 speakers, has generously agreed to run the slides today. To begin, though, I'll offer just a few words on the question of bioenergy climate benefit. The presumption of today's webinar is that there can be both good and bad bioenergy. As the EPA recently stated in the preamble to the new carbon pollution rules, the climate footprint of bioenergy is, quote, sensitive to the type of biomass feedstock used and the way in which the feedstock is grown, processed, and ultimately combusted as a fuel for energy production. This is based on their 2011 finding that biomass electricity is not a priori carbon neutral. In other words, it cannot be given a free pass on a belief that plants will regrow. So how is it that we go about discerning good and bad bioenergy? One powerful tool to help tell the good from the bad is carbon life cycle analysis. So, our 2 expert speakers today will help us understand this tool better. Our first speaker, Dr. Jesse Daystar, studied pulp and paper engineering and chemical engineering at North Carolina State University. As an undergraduate, he worked as the technical director of a project evaluating biofuels and developing ethanol production methods. Jesse's first undergraduate research project involved conducting a series of experiments analyzing different biomass feedstock pretreatment methods for improved ethanol yield. As a graduate intern, Jesse worked with the National Council for Stream and Air Improvement in KZ, assisting in the development of greenhouse gas analysis tools. In 2009, Jesse started his consulting service, Triangle Life Cycle Assessment, to provide environmental assessments of goods, services, and fuels. He was recently awarded his doctoral degree and has published 7 papers on biomass, bioenergy, and life cycle analysis, or LCA. Today, Jesse will give us an overview of the tool of life cycle analysis, including an example. And our second speaker today, I'll go ahead and introduce him. He'll follow Jesse's presentation, is Dr. Adam Taylor of the University of Tennessee at Knoxville. Adam is an associate professor and the extension wood product specialist, and his primary responsibility is to assist those who manufacture and use wood. He's also involved in applied research projects and teaching. Examples of Adam's current interests include improved processing of railway cross ties, phytosanitary practices for logs and lumber, Novel building methods using wood and the life cycle assessment of wood products. Adam will be presenting a pre-publication preview of a life cycle analysis of wood pellets from different feedstocks and for different markets. So now I'm going to turn the webinar over to Jesse, and I'm going to put myself on mute to ensure that everything goes smoothly. Thank you, Jesse.
Great. Thank you, John, very much for the introduction here. Can you hear me well? Hope everybody can.
We can hear you, and I would ask if you can change your screen so that it just shows the slide you're wanting to share.
Okay, let me try setting. Is that any better?
That's black, a blank screen.
We don't want that. How about now?
We see, well, we're seeing the slide and the next slide, but that's fine. I think we'll just go ahead with that.
Now?
There we go. Perfect. All right,
Okay.
I'll mute myself. Thank you.
That's what we want. Great. Sorry for the technical difficulties. As John said, my name is Jesse Daystar, and we're going to kind of walk you through some of the ins and outs of life cycle assessment and how we get an understanding what biofuels might be better for the environment, reducing environmental impacts, and what ones could actually increase environmental impacts. And I really appreciate you saying that, because that really is what my research has found, and I'm glad the EPA recognizes that there's good biofuels and bioenergy and bioenergy biofuels that are not so good for the environment. So to kind of start this out today, I'm going to kind of give you a background of what made me get interested in all this. So as a kid, when I was like 7 or 8 years old, I used to travel from Lexington, Virginia, on the upper left-hand corner of this map, to Lynchburg. And there was a paper mill in Big Island. And I always drove past that and was always very curious to what went on in there. And my granddad actually worked in a paper mill. My dad said, you never want to work in a paper mill. They're bad for the environment. They stink. They're horrible. But, you know, it turns out I was very curious, and I had no idea. So I actually ended up going to NC State and getting a pulp and paper engineering degree, and have worked in paper mills. And from that perspective, I have taken it upon myself to hopefully change the system or understand everything about pulp and paper, and that allows me to reduce environmental impacts potentially. So I figure you can either yell at something or criticize something, or you can learn about it and hopefully change it from within. And that's the approach that I've taken. So that was kind of my motivating factor throughout my life, and even now. So I think it's best to understand and then make the decisions and really shed some light on the situation. And that's kind of how I've proceeded throughout my research. So one point about this is just kind of some quick facts here. Toilet paper, we all use it, and I've seen bumper stickers that say you can't make toilet paper out of plastic, but right now about 3 billion people, so each one of these people is about 1 billion people, representative, use toilet paper. What about the rest? There's 4 more billion people who don't use toilet paper right now, and they might want to into the future as China and India develops and create more sanitary sewer systems. They might actually use toilet paper, but will we have the capacity to accommodate this new production? Will we have the forest? Can we do it sustainably? And tools like life cycle assessment will help us increase production, do more with less, and become more efficient. Because that's going to happen, and whether we do this efficiently and sustainably, we'll find out. Hopefully, we will. And in context of biofuels, it might not be your first instinct to say, "Hey, let's cut down forests to make biofuels." So natural forests are large carbon sinks. They hold a ton of carbon, such as rainforests. And you may have seen out in Southeast Asia that these are being cut down for palm oil production, for biodiesel. And these type of biofuels, the land use change emissions are really large and may not be any better or could be drastically worse than regular fossil fuels. But there might be other ways too, such as managed forests for high growth, and managed harvests, which would take only as much as being planted, so you have a sustainable levels of carbon within a forest to make biofuels. This could be sustainable, but how do we know which one is better for the environment, and how much better may it be? So to get at this today, I want to introduce a life cycle assessment, give you the background of the several major steps. and talk about biofuels and bioenergy, and touch on land use change and some other environmental impacts, and kind of wrap it all up. So the basics of life cycle assessment include four main categories. The first is goal and scope definition, which is the defining kind of what you're looking at, the inventory analysis, impact assessment, and interpretation. And that is all to understand the environmental impacts of a product, services, or good. So I'm going to kind of run you through each one of these steps in the next few slides. So the goal should state the intent of the study, also who's going to use it, who's the audience, why are you doing this, perhaps who's paying for it, to be very clear about the motivation, because that's very important. As well as the scope. What are you looking at exactly? You're looking at a gallon of gasoline, a gallon of fuel, a megajoule of fuel. That's very important. And also establishing a boundary system. Are you looking at cradle-to-grave, meaning from the very beginning of the product, from the raw materials to the disposal, or is it just to the gate, meaning the product as produced but not the disposal? And also you might get at the data collection method. So these goals and scopes are very important to specifically biofuels, and it can really dictate the results. Here's a slide that shows you biofuels from different studies and some results they calculated based upon greenhouse gas reductions compared to gasoline. So on the left-hand side, we have 114% better than gasoline, or lower impacts, all the way down to 50% worse. And on the right side with corn, we have 86% better and 93% worse. This 93%, negative 93%, is a Searchinger et al. Paper, which is a very widely cited paper. I think close to 1,000 or so citations, and it was pretty landmark within the field. And he indicated that biofuels could be very much worse, and that was largely due to land use change. And we'll discuss some of the assumptions that went into that later on in this presentation. So the next step after goal and scope would be life cycle inventory development. So you develop process flow diagrams, understanding where material is going, where is it coming, how much energy you need, and different materials. And you collect the data for that, and you tabulate all the emissions in and out of your system. And from there, you take these emissions and you do an impact assessment on those. So this, the reason for doing this is it helps change a flow of an emission to how that impacts the environment. It also simplifies data sets and makes it more easy to communicate. And the first step of this is classification. You could see here that you have several different emissions on the right-hand side here. We have carbon dioxide and methane, for instance. They're both greenhouse gases and increase global warming potential. So here you can see that they're both categorized as that. And some emissions have more than one categorization. But essentially, you take a pollutant and you translate that to what environmental effects. So you kind of group them together. The next step is characterization. It turns out that methane is actually 25 times worse or more warming than CO2. So you do these characterizations to get to a common unit. And here, typically, CO2 equivalence is a unit which is used to describe global warming potential. So you can see here that 1 kilogram of methane is equivalent to 25 kilograms of CO2. So that's very important to understand, that different pollutants have different impacts to those set categories. So far, we've talked about the goal and scope, the inventory, classification, characterization. I'm talking about it in very brief. We could go hours upon this, but on limitation of today's 20-minute presentation, that's about as far as we're going to go. But I will mention that that is all very objective, but when you get down to weighting and damage assessment, which is additional parts of life cycle assessment, it can be a bit more subjective, understanding, weighting which impacts are worth more to me or to a society. So that really brings in values, and we're not going to go into that today, but it's really a forefront of LCA and understanding how to interpret that. But I will touch on that just a little bit later. So now that you have a basis for understanding of what life cycle assessment is, we're going to talk about biofuels. So I'm not sure if everybody understands the carbon cycle. I didn't actually understand some of this, but until recently. But the carbon flows throughout the environment is depicted in this picture here, and the red ones are actually the fluxes, and the green typed here is the stores. So you might notice down the bottom right that deep ocean has 38, I think they're gigatons, 38,000 gigatons of carbon stored in it, as well as the surface ocean. So that's where a lot of the carbon is, but here you'll see fossil fuels and the atmosphere and vegetation all have gigatons of carbon, and it goes back and forth throughout the system. But what does the biofuel carbon cycle look like? And this is very important to why biofuels might actually be better for the environment. So on the left side here, we have biomass growth, where carbon is taken in from the environment through photosynthesis. And then you harvest that biomass. You might store some of it, depending on its type, transport it, produce it, and combust it in your car. And the carbon that was taken in through that cycle is now released again. And there's somewhat of a closed loop here. There are additional fuels from fossil fuels and chemicals that are released, so it's not a net zero, but the recycled nature of that carbon can introduce a benefit to the environment, as opposed to fossil fuels, which on the right here takes carbon that's been stored up for millions and millions of years and releases that to the atmosphere. So there's no recycle within this, the fossil fuel system. So some of the goals of the work I've done is identify key variables driving the environmental impacts, as well as analyze the influence of feedstock type, land use change, accounting methods, conversion technologies on the environmental impacts of biofuels. And I want to mention here within the scope, 1 megajoule of fuel is a very important functional unit, and that describes what we're comparing between like gasoline and ethanol. But when you're comparing those two, if you were to compare a gallon of gasoline to a gallon of ethanol, it would not be equal comparison because gasoline is actually more energy dense. So to get around that, we compare equal energy units, and that's typically 1 megajoule of fuel. And the work here is going to be cradle to grave, meaning from the very beginning of the feedstock production to the disposal or the use of the fuel. And we're going to look at touch on a few other impacts as well using the Tracy impact assessment method. So system boundary diagrams are very useful to understand what is being included in the study and what is not. So on the left-hand side, I have biomass production, and we include direct land use change, forest management, carbon absorption, harvesting and processing, and transportation. And we actually wrote a publication on that. It was published in 2004. And we used that data to look at different fuel production technologies, and those are modeled using Aspen or different computer programs. And the emissions are modeled by GREET, which is a governmental emissions calculator. And chemicals and other energies are used, data for those are used from the GREET as well as other databases. But I will point out that the indirect land use change is not considered here, and that can be very big, specifically in corn or other agricultural crops. So it's recognized it can be very important, but we did not get into that within this study. And part of the reason is that forest-based biofuels may be less sensitive to that indirect land use change. So here is I'll orient you on this figure here. The bars here represent greenhouse gas emissions for each different stage within this life cycle. So the totals on the left, if you're looking down at the bottom, the labels are there. Feedstock production, conversion, direct meaning like what is coming out of the smokestack of the facility. Conversion indirect would be emissions associated with the production of chemicals somewhere in China or wherever that may be. Combustion and fuel transport is what's coming out of tailpipes. And then electricity would be either you're buying electricity to produce ethanol or you're selling it and perhaps creating an offset. So you notice here that pine, the blue one, it kind of stands out from the rest. And one reason, this is a biochemical conversion of ethanol, and for that, the pine is actually not a very good candidate for that. You cannot do it very efficiently. Its yield is very low. So you ended up not producing a lot of ethanol, but you produce a lot of electricity, which you can see on the right-hand side of that electricity bar. And it actually has a negative emission if you assume an offset electricity, which is not always the best thing. You have to look at a few other different ways to deal with that co-product of electricity, but that is just one method of assuming that you do not produce it elsewhere, and it's called product displacement. But I want to also point out that all those different feedstocks do take carbon in the feedstock production and then release it over in conversion direct, as well as the combustion of fuel. And they all actually are less than gasoline in greenhouse gas emissions, but some are more than others. And when you get down into some further details, really the 100-pound gorilla in the room can be land use change. I think that can even influence more than the feedstock type. So what are the current calculation methods? How does this influence the results? And what biofuel scenarios are more sensitive to this type of emission, the land use change emission, which we abbreviate as LUC? So kind of give you a little background on this. Land use change emissions come from converting perhaps a cropland to a forest or vice versa, and there's carbons stored in root carbon, forest litter, soil carbon, and above ground biomass. as you can see here in this table, there's just a list of different types of carbon stores. And when you convert from a cropland to pine or eucalyptus, you have these different emissions or negative emissions, for instance, on a per hectare basis. So we calculate how much biomass is needed per 1 megajoule of fuel and how much land that is required, and then we calculate what is the emission to make that 1 megajoule of fuel for land use change. So when we examine that, we see here some results. Now I'm going to kind of orient you on this. This is a greenhouse gas reductions as compared to gasoline. So it on the left-hand side are the total gray bars right there. That's no land use change. So pine is about 180% reduction. And when you include land use change, it goes even further up for pine. And I will also point out that the black and white boxes and circles and symbols, they're based upon a 100-year production period, whereas the blue ones are a 30-year production period. And that would mean that the total emissions of cutting down that forest are distributed over 100 years of production or 30 years. So you can see that when you do it 30 years, the impacts of land use change are even greater. And I'll even point out further that down here in the sweet sorghum, switchgrass scenarios, they're very sensitive to land use change. And if you consider the 30-year period, they're actually worse than gasoline. So that's very important. That's actually what Searchinger et al. Found. They found that on a 30-year basis, a payback period, biofuels, if you're cutting down the forests, are worse for the environment. So you release a big chunk of emissions in the beginning, and you don't ever pay it back. So here I'd just like to reiterate that how we account for this emission does matter, and also what we're converting from and to matters, as well as perhaps how efficiently we convert the biomass to biofuels. Another way of looking at this land use change is a payback period, or how long would one have to produce biofuels and for the benefits of that biofuel to offset the initial emission due to cutting the forest. And here we calculated switchgrass and sweet sorghum converting from several different forest types. And when you look at it on a figure here, you can understand how many years you have to produce biofuels in order to pay back that initial positive emissions. So to orient you on this, we have years across the x-axis, and the left is the CO2 equivalents, and gasoline is the dotted or the dashed blue line, and two other switchgrass biofuel scenarios are in orange and purple dots. So the initial emission for the orange line there is roughly about maybe 3 kilograms of CO2 per megajoule, and after a period of time that will continue to increase, but its emission per megajoule is actually going to be lower than gasoline. So eventually those lines will intersect, and the orange line is around 70 years and the dotted line is around 90 years. So the emissions associated with the initial cutting of the forest won't be paid back for anywhere from 70 to 90 years. So is it really reasonable to assume that if we cut down a forest and make biofuels and plant switchgrass to make biofuels, are we going to produce that fuel for 90 plus years? Because not until 90th year will we really experience any benefit from producing these fuels. So it takes 90 years just to break even. So again, this might be a scenario where it doesn't make so much sense. So it's very important to look at that, and it is very sensitive to where your starting position is and your ending position is. But so far we've only talked about carbon, and that is really the focus of today's webinar. But I'd like to also touch on a few other aspects of biofuels' environmental impacts. And there are other impacts beyond just carbon: acidification, carcinogens, eutrophication. Those are all very important things that can even affect us more directly than climate change. These are just the types of impact categories that the Tool for Reduction and the Assessment of Chemical and Other Environmental Impacts list. That's called TRACY, and that was developed by the EPA. So I'm going to show you what that looks like for gasoline as compared to these other types of biofuels. So on the very left-hand side, we see global warming. I showed you that earlier, and I ranked gasoline. Okay, essentially, like, is it worst being 7 or the best being 1? So for global warming, it's the 7th, so it's the highest. But you might notice there over on eutrophication that it's actually better than all the biofuel scenarios. So you might see that if we produce biofuels, we'll reduce global warming, but we might increase eutrophication. So there's going to be a trade-off there, and it's going to be difficult to understand. Is it worth it? And how do we understand that? And how sure are we? And how big is that change? So that is really where the forefront of LCA is understanding this data interpretation, because it's hard to compare one carcinogens to global warming. How do we say which one is more important? So just kind of wrap it up here. It's about 19 minutes in. LCA is a tool used to determine and reduce environmental impacts of products, services, or goods. It's kind of a basic definition. And bio-based products create a complex scenario where carbon is recycled, and that can be difficult to model. There's emerging types of techniques which become more complicated than the past techniques. I think the EPA is starting to integrate those, and that's where a lot of my research is focused. As well as LCA methods greatly influence the calculated impacts, for instance, the land use change emissions and how long we attribute those emissions for. And the use of biofuels will create environmental trade-offs. For instance, eutrophication might go up, but the global warming potential might go down. And that's difficult to understand as well as interpret and decide which is best. And LCA can also help you determine hotspots and understand what unintended consequences may come, and hopefully deal with that and plan for that. And just overall, biofuels can reduce the environmental impacts, but they don't necessarily have to, and it can be done where it decreases or increases. So a life cycle assessment will give you some insight to measure this, quantify this, and hopefully do the right thing for the environment and create a bio-based energy industry that is better, that will reduce environmental impacts. And here's a quote that I just kind of like. It's by Albert Einstein. It's, "All models are wrong, some are useful," and LCA is definitely subject to that. It will never give you an exact answer if the environmental impact is 7.3. That just won't happen. It might tell you a directional thing. For instance, it's 30% better than gasoline on global warming potential, with a 30% to 80% confidence, or some kind of range. But an actual one set number that somebody tells you exactly right is the environmental impact, that's not going to be exactly correct. And but it is a very useful tool. So it's good to understand, what context can we use this data. I'd like to thank the IBIS project, which funded most of this work, as well as the Biofuels Center of North Carolina. And here's my contact information. Please feel free to contact me. We have done some work with Piedmont Biofuels and other product producers, and if they want to know their environmental impacts. So I appreciate the attention today, and I think there's going to be questions either now or later, but I look forward to answering those. Thank you.
Jesse, thank you so much for this excellent overview of life cycle analysis. I think it was a really helpful introduction.
Great, thank you.
And I do want to take a moment to just ask people to make note of your questions, please. Again, type those in through the Google Plus event interface where it says "Say Something," or at YouTube in the comments section, and we'll handle all those questions at the end. I really hope that we'll have some good questions from the audience. That'll make a good, interesting discussion. So now we'll move to Dr. Adam Taylor of the University of Tennessee at Knoxville. Adam, can you unmute yourself?
Unmuted. Hope you can hear me.
All right. Yes, we can hear you, and now I'm going to ask Jesse to start your slides. That's great. All right.
All right, well, thanks for the opportunity, and I'm pleased that, John, if you can unmute your face or something, or mute your face, because I don't see my slides, just if you don't mind. Anyway, I'll try and remember, but so far I'm still looking at John, which is okay, except I'll forget what I'm supposed to be talking about.
Can you see the slides now, Adam?
Yep, that looks great. Thank you. Yeah, as I was saying, I think this is a nice fit with what Jesse had to say, because I'm talking about a fairly mundane, actually, application of life cycle assessment, but something that was of interest to my co-authors and me, and I'll introduce those guys. Janus Kirch is a professor at the University of Ljubljana in Slovenia, where they have a large forest and not much utilization, which is familiar to people, or utilization, but with the potential for more, and that's familiar to people like Don Hodges, who is a professor here at the University of Tennessee, sort of working on policy and some economics related to forestry, and me, who was introduced before as someone who's trying to promote wood use of all sorts. But we were thinking about the rise of bioenergy, and specifically, and as I'll show some slides about in a bit, pellets. And I'd done some simple life cycle models of wood pellets and from the traditional sources, but there's been a lot of change in the wood pellet industry, and as that change comes, so do questions about sustainability and whether this is a good thing, this change that's occurring. And so Don and Janis and I were thinking about how you might go about trying to address that question. It's a very complicated question, as Jesse mentioned, and I'll mention sort of my perspective on some of the questions that come up. And really what I want to look at in these slides is one way to address one component of those many questions, but something that I think is potentially pretty practical, especially in light of some of the application of LCA. There's certainly been a lot of development in life cycle assessment methodology, but also the databases are large and growing, and some of that information is starting to be applied by policymakers, and policymakers are certainly very much responsible for the acceptance and use of biofuels, and so very likely those two applications by policymakers will come together. And so this was meant to be just sort of a small tool in the growing toolkits of policymakers as they look to try and make good decisions. This is the rough draft of a paper that we're working on, and so not only do I welcome your questions at the end, but comments, suggestions for making the paper any better would be greatly appreciated. So Jesse, if we could move on to the slides 2.
Sure thing.
So the wood pellet exports are exploding from the United States and from Canada. Wood pellets have been around for a while as a domestic source of convenient firewood, really. So in the United States, for example, wood pellets are used by homeowners as a way of heating their houses in the winter in a way that doesn't involve lugging big chunks of firewood into their house and getting bark on the carpet and that sort of thing. That really has been the traditional application, and the traditional source of raw materials has been from the hardwood flooring industry, where they bring in kiln-dried hardwood lumber. Half of it comes out of the factory as hardwood flooring, and the other half ends up as trim blocks and sawdust and such, and that can pretty easily be ground up into a nice dry clean powder and run through a pellet mill, which creates a densified wood pellet. There's no real additives to it other than the sawdust and heat and pressure, and that makes something that looks like rabbit food that you can burn in a wood stove with a thermostatically controlled auger and such. So it's very convenient. But that's the old, and the new is in response to subsidies, not subsidies, but policy mandates in Europe, and especially active in the UK, as shown in this graph, encouraging users, commercial, industrial users, to convert from coal or other fossil fuels to biomass sources. And one of those possibilities is wood pellets from the U.S. Southeast. The U.S. Southeast and the growth in that has been because we're a low-cost producer of wood fiber. There's a little bit of slackening demand for traditional pulp and other low-grade applications of wood. And so the growth has been in converting round wood, so not residues from the hardwood flooring industry, which are more or less a finite resource, but to a very much larger potential resource of logs being ground up, dried, and made into pellets. But it's a different process and a different application, but it's exploding. Even though it has the same word, it really is a very different biomass. Can we go to the next slide? These are just some slides I pulled off that awesome EIA database. Just so much great information there, but here's some on pellets. So here it just shows you just over the past few years, that is an explosion to my mind. A lot of the wood from Canada is coming from the West Coast, but in the United States, the big growth area has been in the U.S. Southeast, where I live, and so that's kind of why it's on our mind a little bit. Next slide, please. So here's just taken off some people who are, the website of some people who are not in favor of this concept, showing the movement of wood from particularly the coastal areas of the United States, pelletizing the wood, moving it over to Europe. And if we can go to the next slide, please. So there's a lot of questions about whether this is a good idea, and a quick cruise of the internet will show you lots of people who don't think it's a good idea and a few defenders. And one of the points that I want to emphasize, at least in our paper, is that there are many components of concern to the question of whether this is a good idea. And I'm using sustainability as proxy for a good idea, and that in itself may not even be true. But if you look at some of the concerns that are coming up about wood pellets or biomass in general, you'll come across some of these. There's probably others, but deforestation, see that slide that I've put on the bottom there. That's what comes to mind a lot of times when people think about using wood at all, but certainly when they think about biomass also. We don't address that in our analysis. That's a separate issue about how much wood goes in and out through photosynthesis and utilization, and that's a different topic. My own perspective is that we have the potential to produce way more product from our wood supply. The forest in the United States is and has been growing for a long time. So, my personal perspective is that we have the opportunity to use a lot more wood for various reasons. But what I'm talking about today isn't looking at that. Another issue, and this is one that gets emphasized a lot if you look at some of the critics of wood pellets, for example, and that's issues related to what you're doing to the forest, not so much as it's still a forest, but you might be changing it from hardwood to a pine plantation, or you might be, logging in sensitive sites, wetlands, where you're disrupting some particular organism. And so concerns about what the process is doing to the production site. And this analysis that I'm talking about is also deliberately excluding that very difficult issue. That'd be highly site specific, and there are people who have been working on developing sustainability guidelines for biomass harvesting. But this is very similar to concerns about forestry and other land uses and the impacts on the environment, which certainly not a subject that is distinct or special to the biomass thing, but it certainly is going to come up again as people think about potential new uses for wood. One that I'm calling opportunity cost is a little bit hidden, but it comes up, and I think it is an interesting and important issue, and that's, for example, expressed itself in concerns about wood pellet utilization is, well, you're going to take saw logs and you're going to grind them up and make pulpwood, and that's really not a good thing to do with something as wonderful as a eastern hardwood saw log. And so the idea is that the United States risks becoming kind of a banana republic where we export our raw materials in low-grade form and other people do good things with them. So similar concerns with log exports, but kind of making a low-grade product, which is pellets, out of potentially high-grade material. And of course, there's economics that come into play there, and the other markets that are in the mix along with pellets. And when you have a subsidized in some way, and in this case by policy mandates in Europe, marketplace, it does tend to influence the market. Now, my own feeling is that at least at the moment we got so much low-grade wood, we don't know what to do. So any other application of low-grade material would be welcome. But that what else could happen to that wood potentially is an important issue, which we are again deliberately excluding from this analysis. Finally, and perhaps most importantly, as Jesse mentioned, this issue, what I'm calling carbon dynamics. If you cut the trees, you lost some carbon from the site. Does it take 30? Does it take 100 years to sort of catch up with the trees growing back and sort of balancing out that? And indirect and direct land use changes, and what if you take corn out of production and grow trees, and so people can't eat in another part of the world. And I mean, one of the problems with that kind of analysis is that it just becomes immediately immensely complex, and I applaud Jesse's patience and ability to try and wade into that. I certainly don't have the wherewithal to try and deal with the many wrinkles that go along with that kind of analysis. So again, we're not looking at any sort of change in carbon stocks over time and any carbon payback period or anything like that, any interest rate or any land use comparisons and anything like that. We're going with a very convenient and simplistic assumption that we have sustainable forest management, which over the long term means that the carbon on the landscape as a whole doesn't change in the forest as a result of biomass harvesting. And that's a, perhaps a laughably simplistic assumption, but two things. One, it makes possible some practical and simplistic analyses, as I'll show later. And also, when you compare it to 300 million-year-old fossil carbon, 100 or 30 years doesn't start to look so important anymore. But I will acknowledge that that is a big thing that we're doing, excluding the dynamics of carbon that take place. So if I'm excluding everything, what am I going to talk about? Well, I'm going to talk about carbon leakage, which is the idea, and Jesse did mention this a little bit also, of it takes some energy to make some energy. And the sun photosynthesize, provides the energy, and the plant, the tree, photosynthesizes it, and so it's making some energy, but the process of pelletizing and transporting the pellets also takes some energy, which is associated with the release of carbon into the atmosphere. And that input energy, we can call that the embodied energy, or the embodied carbon if you want. And what we're interested here in is quantifying the fossil carbon, so the gasoline that runs the chainsaw, the diesel fuel that powers the skidder, and the coal that makes the electricity to turn the pellet mill. All those things, in a way, take away from the net potential carbon benefits that you get by harvesting solar energy and using wood as an energy source in place of fossil. So that's really what we're looking at, is trying to account for that leakage, the fossil carbon that goes into biomass, which you're then using to displace a fossil carbon in the first place. So Jesse, if we can have the next slide, please. So just quickly going through the methods here. Again, it's a focus on fossil carbon, and I hope that's not a confusing term, but it's just to contrast. What we're counting is oil, coal, natural gas, and we're not counting, at least as a penalty, the biocarbon, which is the photosynthetic product that's captured in the wood. We used a life cycle assessment type scenario where we measured all the inputs and outputs. Not all the outputs, we did measure them, but the only one we're concerning ourselves with is carbon, which we're expressing, and Jesse mentioned this impact category of the global warming potential, or it's going to be expressed as kilograms of carbon equivalent. But when you're talking about biomass and wood, there really isn't a whole lot of methane and that sort of stuff that you need to worry about. So it really is carbon in and carbon out, but we're focusing again on the fossil carbon. So we use 3 scenarios to kind of demonstrate the hot spots of biofuels production, and also to provide a simplistic scenario for showing our kind of accounting scheme. So the 3 scenarios were a highly processed biomass source, which in this case is wood pellets, and that's highly processed in contrast to wood chips, which if you just take a log and run it through a chipper and burn that material in its green form, which is actually very commonly done. But so pellets are highly processed by comparison. But again, a lot of those biofuels that Jesse was talking about, ethanol and such, those would be even much more highly processed. So highly processed means pellets, and little processing means chips. The other variable in our scenario was long-distance transport, which is from the U.S. Southeast, or local, which in this case is within the EU, where these policy mandates are taking place. So in our case, it was Slovenia, because one of the co-authors is from there, and the destination is Italy in all 3 cases. So next slide, please. So here's the result. Scenario 1 is the highly processed and long-distance transport, so these would be pellets from the U.S. Southeast. Scenario 2 is pellets produced in Slovenia and moved to Italy. And Scenario 3 is in-woods chipping of wood that was moved, the chips are moved to Italy. And you have kilogram of carbon equivalent on the y-axis, so that's just kind of how much fossil carbon, how much gasoline, coal, electricity generated from coal, and diesel fuel, that sort of thing, is used in the various components of these various scenarios. And so the big ones that you see are the transport, which is the big blue chunk in Scenario 1. That ocean-going transport does cost something. And then the pelletizing, which includes drying. In this case, we're talking about round wood, but also the electrical motor, and all of the background data are available. But this is just kind of a summary. And what you see is that it takes a lot less to use low-processed biomass locally, and that's an intuitively obvious statement. But this attaches some numbers to those, and these numbers are based on the growing body of life cycle inventory databases that are around the world. So these numbers are not just made up, although we do have a lot of assumptions underlying the scenarios. Next slide, please. So the previous slide showed that, you know, some bioenergy sources, some wood pellets sources are better than others, as Jesse mentioned, but let's keep our eye on the prize of if we use this wood energy in place of traditional fossil energy sources. And so on a same amount of energy out basis, this graph shows you that regardless of what wood energy source you use, it's a whole lot better than burning coal to generate electricity is the assumed thing here. But it's all based on equivalent energy basis. And so you can see that, yeah, wood varies, but it's way better than the fossil alternative. And that's one of the things that I like to try and point out to people is that, yes, of course there are differences, but the comparisons that you make are vitally important. And compared to a fossil energy source, wood is good no matter where it's coming from or what you do to it to get it there. Next slide, please. So based on those, particularly the first slide that I showed, the graph with the various scenarios compared, or the second one, I suppose, you see that there are differences in how much fossil energy went into making these various energy sources. And what we're suggesting, kind of the idea here, is to be able to apply those if you had a carbon credit for bioenergy, or the flip side, a carbon tax on fossil energy. You could account, using life cycle inventory data, to you could account for the fossil energy that's embodied in the bioenergy source. And here would be an application. So if you had $100 per ton of a biofuel credit, then the fact that there's a 20% of the energy value was required in form of fossil energy inputs to make that, then the idea is that you discount that credit by that proportion to give you an $80 per ton total credit. And of course, you know, it would vary depending on the fossil energy intensity of those biomass energy sources. So you could apply this to wood or any other biomass source wherever it's from, based on life cycle inventory data, and, you know, set up the rules so that you're treating all sources fairly. But if it's coming a long way and it's highly processed, it's going to get less credit based on this, because you're getting less net benefit from them. And of course, coal, in being entirely a fossil fuel, is not going to get any credit at all. Next slide, please. And this is just the flip side of the coin. If you had a carbon tax, which is politically unpopular, of course, in this country, but would be relatively simple. But regardless of your thoughts on it, if you had a tax, then you could discount the tax by the amount of net bio benefit you're getting by using a wood or other biomass source. So if it's coal, you're paying $100 per ton. Wood pellets, you're not going to pay nothing, but you're going to pay something for the fossil fuel component that's embedded in the biomass source. So next slide, please. Which brings me to the subject of environmental product declarations, EPDs, which I mentioned before. The use of life cycle inventory and life cycle assessment data is growing, and this is sort of how they're being applied. And if you think about a food label on Rice Krispies telling you how much salt and sugar and fat are in there, you know, it's standardized and simplified data of interest potentially to the consumers. You could do the same thing for energy or any other environmental variable related to a particular product. And these are such labels are starting to be required for some products, including wood products. And so as the quality and amount of information grows, the use of the data is being increased. And so these EPDs are coming, and EPDs, or the data that's contained within an EPD, could easily be applied to adjust any credit or tax that you wanted to for stored or embodied fossil energy. And one of the things I want to point out is that life cycle assessment is a standardized process, but EPDs even more so. And when you write an EPD, it's based on what's called a product category rule. So if you had, it's basically a set of rules for how you're going to do the analysis for the various components of interest in your EPD. And so if you were going to have a biomass EPD, you'd have to have a biomass PCR, which would say how you're going to consider things when you calculate how much embodied fossil energy is there, or whatever else. But you could include the need to list embodied fossil energy, which would then make it quite easy to adjust tax credits or taxes to account for fossil energy component. Next slide, please. Which I believe is a summary slide. Yeah, this is, I just cut and pasted out of our paper, and I won't read them, but I'll let you, while I speak in the background, and say that we just did a simple scenario based on real data showing that transportation distance and the amount of processing that you do to wood energy systems is important in terms of the net carbon benefit that you're going to get. And using life cycle approach like this, you could easily adjust any tax credit or carbon tax to account for the embodied fossil energy. And again, this is not a sustainability analysis. It doesn't answer the question of whether wood or pellets or anything is good, but as policymakers start to try and evaluate and apply life cycle and biofuels into the real world, tools like this might be helpful. So that's sort of the subject of our paper. I think maybe I have one last slide, which is a joke, perhaps. Yeah, so let me just say thank you for your interest in this. And again, I would welcome any questions or suggestions for the paper to try and make it better. So thank you.
Great, Adam. Thank you so much for that presentation. Can you hear, folks, can you hear me?
Yep.
Yes.
Okay, good. This was two very in-depth and very informative presentations, and I'm looking for questions now. We do have a question from Kelpie Wilson regarding Jesse's presentation. She asks, does the Tracy method not include water, and what about biodiversity?
That's a great question. Biodiversity is definitely an issue, specifically for if you're getting in the forest and harvesting, and water is definitely an issue too. There are impact assessment methods that do attempt at getting towards that. The Tracy method, the version that I used, does not include both of those. The newer version, which most recently came out, does not include biodiversity, and I don't know if it does water or not, but I know that a lot of the databases that are used for LCA are increasing their ability to track water, and the water issue is it's really complicated too, because use versus borrow water, for instance, like paper mills, they take some in and give it back out, and understanding all that can be very complicated. So that is an area within life cycle assessment which is being developed quite heavily right now, actually.
And I have a question, actually for both speakers. Adam, I read one of your prior papers, not the one you present today, but I'm pretty sure that you had incorporated in consideration of the global warming potential of methane, the methane in natural gas. Is that correct?
Yeah, it's all in there.
Okay.
It's automatic. I didn't do any of the counting, but it's included in the database.
Okay, I see. So it may be a database problem, in which case we may need to take this to the national lab that worked the database. But the question for both of you is, with regard to the 25 times greater warming potential for methane, that was from the IPCC, dated back to 2007, and I was wondering, either one of you were aware that in 2013 the IPCC reported revised numbers on methane's strength at climate forcing. And that is 34 times more potent over a 100-year time frame, or up to 86 times more potent over a 20-year time frame. And that was in the Working Group 1 contribution to the 5th assessment report published last June, the physical science basis report. And Jesse, I wondered if you might kind of, I realize this, I'm asking you to do some hand waving here, but could you speak to the possible impact of how that might generally change some of the life cycle metrics that you presented?
Yeah, that's a great question, John. And you point out some very interesting points about methane, the 20-year versus a 100-year kind of time basis. And that really gets into some interesting parts of dynamic life cycle assessment, or understanding how carbon and the warming effect increases and decreases throughout time. So methane actually, as a little bit of background, degrades a lot quicker than CO2. So if you look at it, but it's much stronger. So it's initially very strong and then quickly degrades. So on a 20-year basis, there's still a lot of methane. There's more methane left, and the impact as compared to CO2 is greater. And that's pretty interesting. I actually haven't updated these numbers to the newest report. This was done actually a little more than a year ago. But to really answer your question of how that would impact the results, it would not be very great, because I think I calculated out the overall emissions for all this, and it was about 1% of the greenhouse gas emissions were associated with methane. So it's a very small part of this. But if you start looking at other things, maybe converting wetlands, I think a lot of methane is associated with release of peat and such as that. Those type of emissions, that could be really great. Or maybe products that end up in landfills, wood products, because they often they'll be decomposed anaerobically in part to methane. So that'll be really sensitive to, like, maybe paper or old building materials that end up in landfill. Those types of scenarios will be much more sensitive to that updated methane number.
Mm-hmm. And Adam, the same question. So how would this new methane GWP, global warming potential, how might that shift your findings in the fossil inputs of pellet production?
Well, it would be a fairly indirect, although it could be a fairly sizable impact on the numbers that you get. So, for example, as the source for electricity generation changes in the United States from coal a bit towards natural gas, then if the net effect of that, which we assume is good, ends up being bad because of the methane leakage, for example, from the harvesting of natural gas. But if it impacts it one way or the other, then the number associated, say, with the pelletizing process, which is electricity intensive, that could affect the number. However, I would say that wood will still be good. I doubt that would change for the scenarios that I presented. And secondly, that's exactly the kind of adjustments and data sensitivity that can be accommodated by taking a life cycle inventory approach to trying to count these things rather than make value judgments based on sort of, well, it's not going to be good because it's going to take some natural gas. We need to count these count what can be counted anyways. And I think the net result in my case would be low, but you could still make that accounting and be effective.
And so I'm basically hearing you say that while we can speculate and think about this, and maybe you as our intuition, or you two can as learned users of these tools, it's really important that we actually run the numbers before we speculate. Is that right?
Yeah, I think that's fair. And one of the things, with if there's an update to the forcing numbers for methane, that will be accommodated by things like updates to the Tracy model, which both Jesse and I used, and which could be used in a systematic, in a PCR, which model you used and which version you use would be laid out. So these things can be relatively easily accommodated as the data availability improves.
Mm-hmm. Okay. And I have an additional question, but let me check very briefly to see if we've got more questions from the audience. I'm not seeing either there. So, Jesse, you had mentioned briefly, I think it was in your conclusions, that a complexity that is introduced with LCA, more recent complexity, is that as bio-based materials are being increasingly recycled, that is going to make life cycle analysis more challenging. Could you speak a little bit more to that?
Yes, certainly. I think there's kind of two parts of this. I was referring in that slide bullet to the aspect of temporary carbon storage, the benefits of that, and how you might chop down a tree, make a product, and then eventually that product may decompose or be burned into CO2 again, and it gets somewhat captured. So that cycle is somewhat complicated, and with dynamic LCA, or accounting for these fluxes throughout time, has become even more complicated, and that's really where the science is going, and it's the cutting edge of global warming potential determination. But as far as recycling products, as like, say, paper recycling, that does become very complicated, but that's been complicated since the beginning, and again, with this dynamic LCA, it's also increasing, and there are ways to do that. FICAT and NCASI has actually developed some great tools that National Council for Stream and Air Improvement has developed great tools to capture this, but when you're modeling paper, for instance, you can only recycle paper about 7 times before the fiber actually is too short to use and is going to be sewered or landfilled. So you have to understand, what percentage is being recycled, what is it going to, and downcycling, upcycling. So it does become complicated, but that's really where the rigor and the expertise of somebody who's specialized in paper LCA or understand these systems really comes into play. And it's some of the higher level end of life is what we call that. That's really where the more technical aspects of LCA lie, and it can be very complicated.
Mm-hmm. Mm-hmm. So, kind of a comment, actually, regarding Adam's presentation. I really appreciated, Adam, how clearly you conveyed that the transportation distance and the process energy inputs really are quite important to determining the climate benefit of wood pellets or biomass for energy. And I'm wondering, what were kind of some of the reactions that you've heard so far from within your outreach community in Tennessee?
Well, I haven't this is the first glimpse to beyond the three of us of this paper in particular. But as I work in extension and talk to people about biomass, of course, it depends a lot on who your audience is at the time. But I do hear a lot of people interested in trying to make money off this, and that's maybe unrealistic in some cases, given the market and some of the things that are driving the market and our proximity. Because if the transportation distance is not only an environmental impact, but it's a big economic driver for the stuff. So it's one of the things that I end up talking to people a lot about, is that for a low-value product like wood energy, it's the transportation distances become big economic barriers in addition to having environmental impact associated with them. But I guess people, they have their feelings about the use of wood in general. A lot of the audiences that I talk to are in favor of using wood, just because of the nature of the audiences that I'm talking to. But I'm aware that there is some skepticism about that we might just be raping the earth in a new way here by developing new unmanageable appetites for wood in various ways. But you get the range of opinions depending on who you talk to.
Mm-hmm. And Jesse, I wonder, you and I had emailed offline about the new developments of solar photovoltaic farms, very large installations of PV, solar generating equipment being installed, especially in North Carolina, on the order of 50 to 75 to 100 acre plots.
Mm-hmm.
In some cases where forests are cut, standing timber is cut, typically tree farms rather than naturally regenerated stands. And I wondered if you had any additional thoughts on that, about particularly how you might approach such an effort if you were to examine that question of how the climate benefit might shake out on clearing a stand of forest for 30 years of electricity generation during daylight hours.
Yes, John, that's a great question. It's sort of similar to clearing a forest to produce switchgrass, but it's going to be some different dynamics. So I think with the solar, you have to include the emissions of the solar panels themselves, but that's nothing new. You also compare the savings for each year you're producing or each unit of energy. So it's going to be so much less, X number of kilograms of CO2 less than perhaps coal or your other average grid alternative. So each year you're going to have a certain amount of savings. But in the beginning, as you mentioned, you're going to have a large increase in CO2. So it's a bit of a payback period thing here, as I mentioned to you. Eventually it might pay back. So you're going to have initial high emission, and then each year the negative emission associated with using solar instead of coal, for instance, will eventually decrease that number to zero and then perhaps negative, or being as a benefit. So you might do something like a payback period, and typically, kind of getting a little bit further into a new topic is dynamic LCA. I mentioned it, and that is getting at that emissions today are not the same as emissions in 20 years. So emissions that happen today are going to be more harmful than emissions that you might have 10, 20 years from now, or that kind of works in reverse. Emissions that happen today, or savings that happen today, are going to be better than savings that are happening in 20 years. So discounting these emissions into the future from the solar is actually another component which is very important, and that's getting at the dynamic LCA, and that's going to be a more accurate representation of the impacts than assuming that 10 kilograms of CO2 100 years from now and 10 kilograms of CO2 today are the same thing, because they're not.
Mm-hmm. Very interesting. Well, we have reached the point where we have 15 minutes left in our window for this webinar, and I'm not seeing any additional questions from the audience or participants. So I would like to take a moment to thank Dr. Jesse Daystar and Dr. Adam Taylor for their participation, for sharing their time and their expertise on this webinar. I'd also like to thank everyone who was on the webinar for joining us today and for the question. I do want to suggest that for folks curious for more information, please check out our website, www.cleanenergy.org. In fact, Jesse, if you might put that final slide up for me, I'd appreciate that. Today's presentation has been recorded and will be available both on YouTube and on the webinar archive page of the SACE website, Southern Alliance for Clean Energy. We'll also send you a link to that recording once it has been processed. We appreciate your support and interest and hope that you'll join us again. And thank you all for your participation in this webinar today. We'll now end the broadcast.